a computational approach to packet classification. Hi, my name is Alon Rashelbach, and this is a joint work with Ori Rothenstreich and Mark Zilberstein from the Technion, Israel. Network functions such as access control, quality of service, packet forwarding, firewalls, and many more classify packets in everyday life. Packet classifiers look on the header of each packet and decide what to do with it according to a set of rules, each with several fields, such as source and destination IP addresses, source and destination ports, IP protocol, and more. For instance, OpenFlow 1.4 supports matching up to 41 distinct header fields. Each field can be exact match or have wildcards, such as longest prefix or numerical ranges. Rules may overlap, so the classifier selects the rule with the highest priority. Classification can be performed in both hardware and software. Hardware classifiers are possible thanks to a dedicated component named Ternary Content Addressable Memory, or TCAM, which is a power-hungry ASIC that performs classification in a single cycle. We focus on an alternative, software classifiers that use commodity hardware instead of a dedicated middle box. Classification algorithms usually take part in virtual switches. So let's look on our virtual switch. We gave it some set of rules, and now it's busy classifying packets. Everything is okay, as long as there is only a small amount of rules. When we try to add more rules, we get a drop in throughput. And it doesn't matter which classification algorithm we're using, all experience the same phenomenon. Large rule sets spill out of CPU core cache, causing expensive L3 cache accesses. Just to understand the impact, L3 cache access time is 10 times slower than that of L1 cache. This is devastating for packet classification. You may ask yourselves, how bad is it? Well, let's look on a real example. Tuple merge is a state-of-the-art algorithm that uses hash tables for classification. It requires the same amount of computations regardless of the number of rules it holds. The only thing that changes is its memory footprint, which you can see on the left. Note that large classifiers, meaning 100,000 rules and more, spill out of L2 cache. On the right, you see the throughput of the same classifiers. By the way, these experiments were performed using the standard class benchmark for packet classification. Notice the performance drop of the largest classifier, which is the rightmost point in the right graph. It is twice as slower as the smallest classifier. As mentioned before, L3 access time is 10 times slower than L1 access time. We make the following three observations on packet classification. The rule space is sparse, meaning the actual rules are only a tiny fraction out of all possibilities in all fields. L3 cache and DRAM accesses are the major bottleneck, as they're not integrated in the CPU core. And hardware trends toward commodity accelerators, such as wide vector processing engines that make computations much faster. These all make us wonder whether packet classification may benefit from trading memory accesses for computations. A similar concept was proposed in the world of databases and index structures. The technique is called recursive model index, or RMI for short. The concept is simple. Instead of using bit trees for indexing key value pairs, use a machine learning model. RMI trades memory accesses of index structures such as bit trees with neural network inference. And it's successful. It occupies only 1% of memory of the bit tree, resulting in 2.7x performance gains in databases. The concept is to take a key value table that is contiguous in memory and look on the keys and the memory offsets as a continuous function, say fx on the right. RMI takes representative keys, which are the colored squares on the left, and uses them to train a model that approximates the key offset function, f hat x, orange C on the right. The training technique of RMI performs an exhaustive scan over all keys and checks their approximation error. That way, RMI guarantees that approximation error is bounded by some constant, say epsilon. An RMI model consists of multiple submodels in a staged fashion. Each submodel can be a neural network or a bit tree. All submodels do the same operation. Given an input x, they try to approximate f hat x. Only a single submodel is evaluated per stage. The outputs of internal stages are used to choose a submodel in the following stage that has a better chance to be successful. You can say that submodels in deep stages handle less inputs with more expertise. Let's see an example of how RMI works. We have a key value table that is contiguous in memory, and say we trained an RMI model by representative keys, which are again colored rectangles on the right. Now we wish to find the corresponding value for the key 68. We feed it to the model and get an approximation for the memory offset. F hat x equals 104. Let's say we know that approximation error is bounded by epsilon equals 2. So we go to the table and perform a secondary search over the keys around the model approximation. So this is how RMI works and trades memory accesses with computations. Now, we ask ourselves whether RMI is suitable for the job of packet classification. The answer is no. And the main reason is that RMI does not support wildcards. Let's see it in action. Let's take a toy example of classification rules with only a single field, destination IP address. Say we can somehow represent these rules with the function fx, which is far from trivial, but for now, let's assume it's possible. Notice that the keys are now ranges. IP addresses may contain wildcards. We take representative ranges, again colored rectangles, and try to train an RMI model. This is far from trivial, and there are many unanswered questions. For instance, how many samples do we need to take per range? For simplicity, let's say it's enough to take some set of samples and everything works and it's okay. Remember, we must bound approximation error of the RMI model, and we do it by iterating over all ranges and check the approximation error. We must provide a correct bound for all possible inputs, even those that did not take part of the training. This is almost impossible and extremely inefficient when facing ranges. For instance, the last rule alone expands to 16 million options we must check. Add the fact that rules overlap and their high dimensionality, and you get a huge RMI model that does not fit in core cache, a slow and almost infeasible training process, but mostly an exponential blowup. We have three issues that cause the exponential blowup: wildcards, overlaps, and high dimensionality. We solve them all by using range query RMI models, or RQRMI for short. We overcome wildcards by approximating range value pairs instead of key value pairs. We overcome overlaps and high dimensionality by using an efficient rule partitioning technique, but most of all, we prove RQRMI correctness and provide the implementation that makes both training and lookup processes efficient and fast. RQRMI models are similar to RMI models in their structure and their purpose. They handle range value pairs by approximating a function representation of the ranges and their position within a table. Similar to RMI, RQRMI contains submodels in a staged fashion. However, in our case, all submodels are shallow neural networks with a single hidden layer and ReLU activation functions. All networks solve the same regression problem. Given an input x, they try to approximate the matching range that contains x. The usage of shallow neural networks with ReLU activation functions is important, as they are in fact piecewise linear functions. We prove in the paper that one can guarantee a bound on the approximation error for the entire input domain using piecewise linear function and sampled training. Unlike RMI, we don't need to check all possible inputs for all ranges, just for calculating the error bounds. More details on the RQRMI training technique, error guarantees, and correctness proofs are available in the paper. We now show a rule partitioning algorithm for handling overlaps and the high dimensionality of classification rules. Let's take a different view on classification rules as hypercubes in an n-dimensional space. Each rectangle represents a classification rule. Each axis represents a field. Using this geometrical representation, we can partition the rule set into several subsets, each with a field with non-overlapping ranges. We term those subsets as independent sets, or I-sets for short. We elaborate on the I-set partitioning algorithm in the paper. Let's look on I-set 1. It contains rules 4, 5, 6, and 3, which do not overlap in the destination IP field. I-set 2 contains rules 1, 2, and 7, which do not overlap in the source IP field. Some rules do not belong to any I-set. We term them as the remainder set. Note that all subsets are mutually exclusive, meaning each rule is contained in exactly one subset. Continuing our example, I-set 1 contains rules that do not overlap in the destination IP address, so we can treat this field as non-overlapping range value pairs and use an RQRMI model to approximate that I-set. Similarly, we can do the same with I-set 2 and source IP field. We cannot use RQRMI on the rules in the remainder, as they don't necessarily have a specific field in which they do not overlap. So we use any existing packet classification technique to handle the rules in the remainder set. Going back to the I-sets, we now know that RQRMI matches a rule on a single field, which is the field of the I-set. What about all other fields? So the key concept here is, once an I-set results with a matching candidate, we know for sure that all other rules within the I-set cannot possibly match the packet. The only thing we need is to validate that the candidate matches all other fields as well. This raises an interesting observation. Adding more fields to the classifier will only affect the performance of the validation phase. It means that the throughput differences between classifiers with 5 fields or 10 fields is practically 5 more comparison operations per I-set. Usually, we have more than a single subset. For example, we may have several I-sets and the remainder set. In that case, we need to evaluate all subsets either in a sequential or a parallel manner, and then select the highest priority match. One question still standing is, how many I-sets do we need? This table shows the percentage of rules in the I-set out of all rules in the rule set. We term this percentage as I-set coverage, and we can see that it's high for large rule sets. For instance, for 100,000 rules, we see that 2 I-sets cover 96% of the rule set. There is an interesting trade-off between the number of I-sets and their classifier's performance. One might think that when it comes to the number of I-sets, the more the merrier. However, it seems that the performance improvement is negligible. This chart shows both the coverage and the classification latency as a function of the number of I-sets. The red line represents the coverage, and we can see how the various classification stages affect the performance. Our measurements show that I-sets with less than 25% coverage do more harm than good in most cases. Now we can put all things together. We term our solution as Nuevo Match. A Nuevo Match classifier takes a rule set, partitions it to several I-sets, and constructs an RQRMI model for each. The remainder subset is classified using any existing method, so we just plug and play. Now, you might have a bunch of questions. For example, can we really fit both RQRMI models and the remainder in L2 cache? So here are cut split, neurocuts, and tuple merge, or state-of-the-art techniques for packet classification. We test the memory footprint using the standard class-bench benchmark for packet classification. Almost all methods spill out of L2 cache for large classifiers. Compared to them, NuevoMatch hardly reaches the bounds of L2 cache. We ran NuevoMatch 3 times. In each time, we use a different method for the remainder set. The red bar represents RQ-RMI models. The orange represents the remainder. Another question, what about neural network inference? Isn't it slow? Well, apparently, with a combination of small and shallow neural networks with wide vector instructions, we can evaluate an RQ-RMI model in between 40 to 50 nanoseconds on a CPU. Another question, what about updates? We can easily remove rules from RQ-RMI models, no retraining required. New rules get into the remainder. For instance, we can use tuple merge, which supports fast insertions. After passing a threshold in the number of new rules, we retrain RQ-RMI models. Our experiments show that training with TensorFlow takes about 10 to 40 minutes on a CPU. However, in our ongoing work, we achieve training time of 1 to 20 seconds using native implementation on CPU. Let's talk about evaluation. We experiment end-to-end performance and detailed analysis of various aspects. In this presentation, we will discuss only the highlighted experiments. The rest are elaborated in the paper. First, we wish to test NuevoMatch's classification performance with skewed network traffic. We know that internet traffic tends to have temporal locality with zip distribution, so we generate synthetic traffic traces accordingly. We use ClassBench to generate 500,000 classification rules and compare NuevoMatch to two state-of-the-art methods, cut split and tuple merge. In each time, we use a different method for the remainder set. So, for instance, we compare cut split against NuevoMatch with cut split as the remainder. You can see that the speedup is highly dependent on the zip coefficient. So we also extract the temporal locality of real-world traffic traces, which is denoted as CAIDA. However, in real-world conditions, the classifier coexists alongside other tasks. So we also test the performance under L3 cache contention, which is denoted as CAIDA star. In practice, virtual switches such as Open vSwitch have caches that catch the temporal locality of the traffic and invoke the classifier only upon cache misses. So we simulate that behavior by testing NuevoMatch using traces with uniform temporal locality. We use ClassBench to generate 12 distinct rule sets with 500,000 rules and compare against 3 state-of-the-art methods. In all rule sets, NuevoMatch exceeds all other methods. The GM on the right stands for geometrical mean. Note that some bars are missing. These are NeuroCut's classifiers that did not converge. In another experiment, we test public real-world rule sets from the Stanford backbone. We compare NuevoMatch against tuple merge, which gave the best performance out of all state-of-the-art methods. NuevoMatch reaches a geometric throughput speedup of 3.5x for traffic with uniform temporal locality. To conclude, NuevoMatch introduces a new point in the design space of packet classification algorithms and opens up new ways to scale it on commodity processors. This is possible thanks to RQ-RMI models that support fast lookup of range value pairs and piecewise linear functions that guarantee RQ-RMI correctness. It is important to understand that NuevoMatch is not operational in a real system just yet. This is the goal of our ongoing work. That's it. I hope you enjoyed the presentation. This video, as well as the GitHub repository and more information, are available at the website. We would be happy to hear your thoughts on RQ-RMI and NuevoMatch, whether by the Slack channel or by email. Thank you.